Hello, my friends of Katray Labs. Welcome to this webinar. Okay, let's have a look on the webinar. So let's have a look on the webinar that we are going to have. So the webinar is on the simulation of pit inflows using MODFLOW 6 and MFC Voronoi. Still, I cannot hear to Raman, but we can have, okay, we can have, oh, okay, let me check. No, actually I cannot hear Raman, but let's work through the chat. Is that possible? Okay, so this is the link to download the files, and the password is Hattery Okay, so let's see, let's download this. Okay, great. So we are going, this is a RAR file. So I have a Windows RAR. So here I have WinRAR. So I'm extracting. Okay, and then we do Control C, and then we paste that on our documents. We paste that on our documents. Okay, so this is the folder, so I am going to do that. Okay, we pasted that on our documents, and then we extract here because we want to extract here. Okay, great. So now we have the folder of webinar, okay, where we have all the files, and then we have that on document folder. So we can start with our Anaconda prompt. CD documents. CD webinar. Okay, and here we launch Jupyter Lab. If you are here with me, please type 1. If you are here with me, please type 1. So this will prompt you to okay, so if you are seeing that with other colors, you just have to change to light, but I prefer to work with dark. Okay, so let's see, let's create a new notebook here on the root that is going to be called part 0. Okay, why part 0? Because here what we are going to do is to do the first part, that is the we are going to work with the templates. Okay, so first we are going to upgrade our Voronoi file. So pip install score capital U mf6 Voronoi. Okay, shift enter. Okay, if you are here with me, Raman, please type 2. Type 2. Okay, and we have already installed in the latest version, that is 0.023. If you are here, Raman, please type 2. Okay, well, so we have uploaded the pip. Okay. Okay, so we are going to say from MF6 Voronoi utils import copy template, okay, and then list templates. Okay, great. So we have this, and then we have a new command that is list templates. Okay, and this new is actually a list of all the templates that we have. We have for the generation of the Voronoi, for the model creation, for the comparison observed and calculated, for the VTK generation, and for the multi-layer transient. That is the template that we are going to use. So we are going to use copy template of generate Voronoi of OpenPit, and this is the prefix. Okay, so this is to copy the generate Voronoi. Okay, copy template of multi-layer transient, that is the one that we are going to use for our transient model, and this is going to be called OpenPit. Okay, and copy template of VTK generation, that is the one that we are going to use for the VTK generation. Now on OpenPit. Okay, so we have run this, and what it does, it creates three files here. The one that for the generate Voronoi, for the multi-layer transient, and VTK generation. So we are going to start with the generate Voronoi. Okay, so here we start with the generate Voronoi. Great, so that is amazing. So warnings. Okay, so this will be OpenPit. The maximum ref is 250. The catchment is the limit. The river basin has 50. And then we have the pit shell, that is where the pit is going to be developed. And the pit will be 50 again. And this is in mine plan pit shell. Okay, so this is just the link to a polygon shapefile that is on the mine plan. Okay, great. So we run this. And we run this. Okay, so we generate the original and the distributed. Then we generate the output. So this will create an output folder. In the case here, it actually exists, so it will delete this, okay, and create again. That's why it's called initiated. Okay, and then here we have the mesh of our basin with the pit. Okay, there is an error here where we only have the pit shell, but we don't see the drainage network. Why? Because the error is here. The layer needs to have a different name, otherwise it will confuse. Okay, pit, this is going to be called pit. Okay, once again, restart. So Okay, and then here we see the pit shell and the drainage network. That is amazing. Okay, and then we read the chef file and we get the properties of the distributed by vertex. Okay, and then we save that as a JSON. That is a folder that is also generated again. Okay, so if you have something on the JSON folder, it will this command will delete it and we create again the folder. Okay, that's okay. So we get it to the part 5. To the part 5 because it's the multi-layer transient. Okay, this is similar. Okay, this is a template for multi-layer and transient models. And it's number 5. Okay, kernel and clear outputs. It's number 5 because it's the fifth template that I have created. Okay, so we have here the get lay cell. There is some thing about the shape. Okay, so we open the JSON and then we got the properties of our Voronoi mesh. Great. And then we open the we need to open the raster, but in this case it's not called elevation, it's called topo WGS 12 north.tif. Okay, so we are going to work with 15 layers. Top will be from the raster and bottom, the bottom elevation will be 1300. Okay, and this is a distribution, okay, that you have to be aware of. Okay, in this case it works this way, but you have to look for the distribution of percentage that actually work with your case. Okay, so this is okay, you can play around with these values. Okay, why 1300? Because the lowest part of the basin is 1600. So, and then we leave 300 as a minimum thickness to the model. So that is why we came up with 1300. So we run this. Okay, and then we on the simulation that is the same. Okay, and on the okay, so we are going to model 20 years every 4 years. We are going to model 20 years every 4 years. Let me check something. On the fourth line, uh, what the grid on the where? In which cell, Raman, are you talking about? Yeah, here in this cell of that extract, cell number 5. Yeah. Okay, where in cell number 5? Ah, okay, okay, okay. Yeah, you're right. This is 0.8. Yeah. Okay, okay. Yeah, my mistake. Okay, so we did that. Don't worry. Yeah. Okay, so this is we are going to model 4G. Okay, we have one steady state and 5 transient stress periods. Okay, and each transient stress period takes 4 years. Okay, so we are going to model 20 years. Okay, so that is amazing. Okay, so this is this, P name this. Okay, so this is 6 years. So we run this. Okay, and then we create a GWF model, and then we are going to do the complex model. Okay, big G stop. We have just to run this, and then this will import the values of the transient, and then we can plot our imported topography. And then we have a shape file that is a cross section, that is a cross section on the pitch shell. Okay, and then we can plot it, the grid on the cross section. Okay, as you see here, we have a lot of layers, okay, in the first part, okay, and then we have just 2 layers on the bottom part, and in all of these layers, this is where the pit is supposed to happen. Okay, so okay, let's talk about the initial conditions. Okay, we are not going to apply the initial conditions of the model top. Why? Because it creates some non-convergence. Okay, so we are going to extract. We have previous run the model, and then we have saved the results. Okay, and then we are going to extract those results. Why? Because it allows us to do the model converge faster. Okay, so for that we run that. I am going to explain later on where you store this. Okay, so this is the initial condition. There is a question. Okay, which is your question? Okay, so why Raman is making his question? Okay, so we are going to say it's 4 times 10 to the minus 5, 10 to the minus 7 for a range of 6. Okay, 3 times for the range of 6. Okay, and and minus 13. Okay, so this is for the first layer, it will be 4 10 to the minus 4. Then for the next 6 layers will be 7.7 10 to the minus 7. Okay, for the next 6 layer will be 3 10 to the minus 7, and then for the remaining ones will be 1 10 to the minus 7. Okay, the easel type, it will be the first 10 layer will be 1, so it will be convertible, and just the last five layers will be confined. Okay, and here there will be anisotropy, so kx equal to kx. Okay, let's see which is the question of Raman. Okay, so Raman, this is my WhatsApp number. Please take a photo of the error so I can help you. Yeah, great. Now let's go to the storage. On the storage, we have that the first one is steady state, and all of them are transient. Okay, and that is okay. And the recharge and evapotranspiration are the same: 200 millimeters of recharge, 1200 millimeters of potential evapotranspiration. That is all right. Okay, we define the intersection of object. Okay, and then so what we want is to get the river. Okay, what we want is to get the river So this is the river. Okay, on the raster. Okay, how this it works. Okay, so we have our model. We have the intersection object. Okay, and this is the river basin. Okay, so we have the model, we have the intersect. Okay, so we are going to intersect the river basin, okay, to the cells where on the elevation on the path of the river basin at the elevation of topo, the corresponding cell. So actually, all of these will be layer 0, okay, but it will do the calculation, okay, and it will create all the river network for layer 0. So that is how this works. Okay, this is how it works. Get the layer elevation tuple from raster. Okay, so for these cells on the corresponding cells it will apply this elevation. Okay, let's see. Okay, now we are going to add more. We are going to add the different bits. Okay, so we are going to import copy because there is a problem of river of inheritance in Python. River SPD of 1 is equal to copy dot copy of river SPD of 0. Okay, so let's say, and then we copy this, Control C, and then we paste it here, Control C. Okay, so we want the from GWF, but in this case is get cell. Okay, for the raster at main plan pit elevation for year 4.tif. On the pit shell. Okay, so it will apply for the cells that are inside the pit shell. It will apply the elevation that is stored on the pit elevation. Let's say for index laser tuple in enumerate laser tuple list. Okay, and then river is PT1. Okay, so we are going to append. Okay, because river SPD1 was a copy of the one of for the first stress period, that was the drainage network. Okay, and then we are going to copy this, append laser tuple. Okay, but in this case, just to recognize, it will be the conductance will be 0.011, so it would, meaning that this come from the first stress period. Okay, for this is for year 4. Now let's work for year 8. That will be a copy, and this will be for year 8, and this is river SPT2, and this will be 2. Okay, and this is for year 3, and this is for year 12, and this is for year 3, this is 13. And the same, this is for year 16, this is for year 4, and this is for year 4. Okay, and the latest one, that is for year 420. Sorry. So I made a mistake here. I have to, this is for year 4. So I'm going to make a comment here just to separate each year. So this is for year 3. Okay, great. Any other questions? Okay, so this will create different set of cells at different elevations for the different stress periods. Okay. Okay, let's see, I will point, this is for year 4, this is for year 8, this is for year 12, this is for year 16, and this is for year 20. Okay, later on you can explore the spatial data. Okay, so this has a, okay, in case of the raster that is above the elevation, so it will point, because there will be some cells where the raster, where the elevation is above the, where the elevation of the raster is higher than this elevation. Okay, great. So we can apply our river SPD, and then we can plot, for example, for the period 1, and then you see, for example, the drainage network, and the, for the period 1, the cells where the pit is active on the first layer. But this is actually not that, it's not that amazing, because you want to see that on cross section. Yeah, and we are going to, the next cell actually creates a cross section where we are going to use the 5 for the, we are going to plot the drainage network for the latest stress period. Okay, and then here you see the pit. Okay, here you see the pit. Okay, the intersected pit in the cross section. Okay, but you see the development of the pit as well. Great, so that is amazing. So, and then we set up the HDS, and then we run this. Okay, if we run it with model top as the initial condition, actually you will get a non-convergence. Okay, but even that, okay, so you store here the non-converged heads. Okay, and then when you run it again, you will get a convergence. Okay, any questions from my friend? Okay, any question from Raman? Okay, so this is 1, 2, 3, 4, 5. Okay, we are still waiting for the 6. Okay, great. So if you see, we didn't find any convergence problems here. Okay, we didn't find any convergence problems here. Normal termination, and then here this will be, these are the stress periods where we have results. We are interested in the latest one, the stress period 5. Mhm. Okay, so we want the, for example, we might want the distribution of heads, but what I am more interested in is um, the distribution of the this is the distribution of the water table and the pit. Okay, so that is amazing. So okay, so we have the model, we have the we can explore the some budget. Okay, but what we are going to do on the latest part of this tutorial, we are going to open the template form for the VTK generation. Okay, and here we are going to open the model. Okay, okay, we are going to create, we are going to initiate the folder VTK. So if there is a VTK folder there, will be destroyed. Okay, and then we are going to list because we only have one model, and these are all the packages, all the packages. Okay, so this is head observation, MFCBTK, get output head. Okay, and these are all the stress periods here. Okay, so we are going to generate the geometries array and the param-BTK. And for the heads, we are going to create the heads for the stress period number 5. And for the VTK as well, the number 5. And for the water table as well, because we want the water table on the last stress period. Okay, what this is working is here. Okay, so actually has deleted the folder that was before, and it has created a new folder where it's storing some values. Okay, it takes some time because actually there are a lot of values here. Okay, I'm going to do a pause on the recording. So here we have created the boundary condition of the drainage and as well the head BTK and the water table BTK. Okay, and these have created these BTKs on the BTK folder. So we can open ParaView. This process has taken around 5 minutes. Okay, so I have paused the video because I want you to see the most amount of the, I mean, I'm going, ParaView has some issue when I do some scaling of the screen, so that is why here I change it to 100. Otherwise it really get a mess. Okay, so let's see, let's open the heads. Let's open the heads. So we go to documents, we go to the webinar and the VTK, and let's open the water table. Let's open the water table. And this is the water table. Okay, we are going to provide a vertical acceleration of 2. Great. Okay, so let's open again and let's open the drainage network. Okay, we do the drainage network, and as well we do a water table of 2, but since we want it a little bit up, so we put it 10 meters above surface, but this is just, and then we can have a solid color of this color. Okay, and here on the water table as well, I'm going to change the we are going to change the water to Bluetooth cyan. and then inverted. Okay, great. So this is the pit and this is the water table. Okay, so we can open the parameters as well. Yeah, it's really nice. Parameters apply. Okay. Um, and then we want to see the K values. And then we want to see another but with the log scale. Okay, so this is the log scale. And then here we can do a cross section, apply. Okay, since there is a streaming and there is a recording, so the process is really slow. So we do the invert, we do the apply. We have to provide again the okay, it's still really low. Okay, and then we go to the K values. Okay, and then we do the then we can do some opacity as well. Okay, great. So now let's open the water table, the water heads. Let's open the water heads. Okay, so we are going to give another Bluetooth cyan inverted. Okay, and here we need to do some filter because we want to plot the isocontours. So we'll say the cell data to point data. Now first we have to do a threshold. So we do a threshold for the, because this is the waterhead of all the cells, but we want only for the cells that are active, the ones that are below the water table. So these are the cells that are active. Okay, then we do the cell data to point data. Okay, we do a cell data to point data. And then we do a ISO volume. This is the procedure, okay, I haven't invented. Okay, this is how it works. Okay, and then here we see the view, and then we can do contours from the ISO volume. Okay, and then we do apply. It will take more time, and these contours we can do some vertical exaggeration. And then here you see a nice interpretation, impact assessment of the pit, the development of the pit, okay, to the, okay. There is still one more webinar or tutorial that will be created where we are going to apply faults, yeah, we are going to apply faults to the model, and then we are going to extract the water table here. We are going to have to assign this as a some budget and the some budget will be we are going to measure the amount of water that will come from here. Okay, yeah, it's nice, it's a nice package, a lot of things will be okay, and all the files will be, or you have it on the description on the model. Well,